Hi everyone, I'm Sunil and I'm going to present my research on enabling practical security analysis of smart homes by creating a natural perspective of home automation. Smart home devices are being used everywhere, and for the most part, their popularity stems from home automation, that is, the ability of devices to work together. For instance, we can make the light turn off automatically after we fall asleep, change the setting of thermostat based on weather or time of day, or turn the security camera on when we leave home for monitoring and turn it back off when we return for privacy. Such automation is generally expressed in the form of trigger action programs known as routines, which execute an action such as turning the camera off in response to trigger such as user coming home. There are generally two ways to create routines. First, we can use GUI interface provided by the platforms where we can simply configure trigger and actions without writing a single line of code. Or we can use IoT apps created by developers, which are often hosted on app marketplaces such as Samsung SmartThings Marketplace. So routines are great, and in the last few years, researchers have built systems to better understand their safety, security, and privacy implications in smart homes. For example, Soteria looks at chains of routines that can put the system in an unsafe state, and IoT Guard looks at enforces security and safety policies dynamically. After studying these systems, we noticed a couple of things. First, researchers specify policies manually by performing use-misuse case analysis for each of the devices. Second, after the system is built, they are evaluated with random events. And more importantly, almost all of these systems study and evaluate marketplace IoT apps, which are created by developers. So when we observe the design decisions for most of these systems, we notice that there are several unanswered questions. For example, instead of imagining use-misuse cases, which is both subjective and tiresome approach, can we specify policies in a less subjective but somewhat automated manner? Similarly, instead of using random events as input, can we use sequence of events that are more representative of how people automate their homes? Also, are people even using IT apps? That is, are these apps representative of what people are using in the wild? And can we study them to actually find real problems? On this topic, one of our findings from preliminary survey does show that more than 42% of the routines created by the users were not even represented by the marketplace apps. So all these takeaways from the prior work point to one critical gap. That is, designing practical systems is difficult because we do not understand how people automate their homes. Let's say we had such an understanding. Let's assume we had scenarios that described what happened in the home. Let's call these home automation scenarios. In the scenario, user comes home, it's evening, so user turns on the gas drains, plays some music, motion is detected, and security camera takes picture. Overall, this seems like a natural sequence of events where user is simply doing their normal chore, possibly after getting back from work. However, there is a subtle privacy violation. We do not generally want security camera taking picture of us while we are at home. Security cameras are generally configured for home monitoring while user is away, but in this instance, the user's motion is probably the cause of picture being taken. So now let's think about how we can use this scenario. One thing this scenario motivates is the security policy. That is, security cameras should be turned off when the user is home. Similarly, if we are able to obtain these realistic scenarios, we can also evaluate security systems better. So we just saw how scenarios could provide realistic glimpse of home uses. However, it's important to understand what we want from these scenarios. First, we want it to be natural. By natural, we mean that it should be reasonably likely to occur, representing how people generally automate their homes. And we want these scenarios to be useful so that we can use it for security tasks like policy specification. Now, to obtain these scenarios, one naive approach could be collecting the execution traces of smart home uses. We tried doing this, but we noticed that traces contain noise associated with platform-specific intricacies, which made it difficult to focus on the semantics of automation. Another thing that we noticed is getting traces from end user's home is extremely privacy invasive because these traces are evidence of what is happening in end user's home. Considering smart home adoption is already slowing down because of privacy, we do not want to make the problems worse. After considering these two problems, we dropped the idea of obtaining scenarios directly from the execution traces and instead went for the practical alternative, which is generating synthetic but natural scenarios. But the major research question still remains. How can we automatically generate natural home automation scenarios? One way to go about generating scenarios is to treat the task as modeling problem. First, we need to answer what we want to model. Since you want to model regularities in home automation, the data should also have those regularities. As we have discussed earlier, user-driven routine is the best option, as these are the realization of end-user programming in this domain and truly captures the requirement of end users. And this brings us to how to model. We want to use something that captures these regularities. Statistical language modeling is a popular technique that's used both in NLP as well as software engineering community for auto-completion tasks like sentence or code completion. So our key intuition here is that since user-driven routines have regularities, we can use language modeling technique to model them. Now let me explain our intuition with the help of English language. Consider an example sentence completion. It is not difficult to guess that the sentence will be "you only live once," even when "you only live barely" is also grammatically correct. This is because it is a colloquial phrase which is repeatedly used. While in theory there are infinite combinations of words, in practice utterances are natural as it contains repetition which enables prediction. One of the language modeling techniques used for this kind of prediction is known as n-gram language modeling, which looks at probability of an event after a certain history. Here, once is clearly the most probable because in a corpus of human conversation, you only live once is going to be more probable. Now, let's use this intuition for home automation events. I walk into my room, light turns on, I walk out of the room. The next event will probably be light turns off, as it is more likely compared to camera turning on or heater turning off. So similar to how we can predict words in English language, we can use the same intuition for home automation sequences if they are natural and have semantic patterns. This leads to our core hypothesis of naturalness of home automation. That is, the home automation sequences created by humans are implicitly natural. That is, they exhibit patterns that make them predictable. Thus, we can use statistical language modeling to analyze corpora of sequences and predict useful scenarios that enable the design and evaluation of security systems. To this end, we present our framework Helion that predicts realistic scenarios. As discussed earlier, we have these user-driven routines, and we want to generate realistic scenarios. So how do we get to these realistic scenarios? First, we need to get some idea of the order in which routines execute. Hence, we take clues from the users, which we call execution indicators. Now, we need to create home automation scenarios using these user-driven routines and execution indicators. We use the process called informed scheduling, which places these routines in a time series that approximates how the user wants these routines to execute. Then we model these sequences using n-gram language modeling technique, which subsequently allows prediction. After that, the model is used to generate realistic scenarios. Additionally, we also develop prototype tools to allow security researchers, platform vendors, and device manufacturers to use these scenarios for security. But to get to generating scenarios, first we need data from users. So we use the survey methodology, which we split into 3 tasks. First, we ask participants to select devices. We provided a list of 70 popular smart home devices. Second, we collected routines. We asked participants to provide triggers and actions in a plain English text, as we did not want to enforce any artificial constraints on routine creation. Finally, we collected execution indicators. Here, we collected time range and frequency indicators to get clues of when and how often routines are expected to execute. Using this methodology, we collected 273 routines and from 40 participants. And just from our preliminary investigation, we found many interesting things about home automation. First, all participants indicated that routines are important to them, which of course motivates our study of automation. Second, IEEE apps could not represent 42% of the routines specified by our users, which means that there is a significant gap in what developers think people want and what people actually want. Furthermore, users indicate a strong preference for creating their own routines compared to solely vendor-controlled automation. Another interesting finding is that users perceived any device as security sensitive. For example, smart outlet was considered security sensitive potentially because a security sensitive device might be connected to it. And lastly, majority of the users were able to provide specific execution indicators despite having an option to select not sure or anytime for each of those routines. Now that we have collected routines in English language, we want to tokenize these routines for modeling. Here's an example of tokenization where security camera takes picture when motion is detected. We identify device attributes and commands for each trigger and action events and create subsequent tokens. So motion sensor is a device, motion is attribute, and detected is an action. After tokenizing all these routines created by users, we move to generating home automation sequences. That is, we take tokens and execution indicators and generate sequences for each user. These sequences constitute the home corpus that we generate through our work. To get home automation sequences, we perform informed scheduling. In this process, we initialize month-long time series, place routines based on time readings, day readings, and frequency indicators. And for the routines where users weren't sure, we randomly distributed them in the sequence. Finally, we combine home automation sequences of all the users to create home corpus. So now that we have home corpus, we need to establish that home automation sequences are natural before we use the model for prediction. That is why we test the naturalness hypothesis, which is the foundation of this work. We use a popular metric known as cross entropy, which measures how perplexed the model is when exposed to the sequence from the same domain. We compared cross entropy relative to English language corpus and programming language corpus. As you can see, the home corpus follows the same pattern in that the 1 gram model has high cross entropy and it goes on decreasing after that. More importantly, this evaluation shows that home automation programs are even more predictable than the traditional software and English language. Hence, home corpus is indeed natural, and we can use it to predict scenarios. Now that we can build the n-gram language model, we can predict scenarios by treating the model like sequence generator. That is, we give it a history and iteratively predict the next event to generate scenarios. We generate expressive scenarios for security using prediction flavors. Here's what I mean by that. The default is generating natural scenarios, that is predicting most likely events. We call this the up flavor. However, to demonstrate situations where events are least likely, we also create down flavor. Our intuition is that generating expressive scenarios will allow us to capture what is normal, as well as instances where the system is misbehaving or under attack. Now that we have established that home corpus is natural and we can predict expressive scenarios, let's look at how they can be useful. For this, first we built an execution engine on top of SmartThings, which can take Helian scenarios and execute them as test cases. The engine generates logs that give us an event-by-event narration of how devices and platforms perform during execution. We also developed the snapshot module that tracks the evolution of states of individual devices and home as Helian scenarios are executed. Our implementation generates these snapshots, which are represented as JSON objects. These snapshots can be examined by the researchers to identify safety, security, and privacy violations. So first, we evaluated Helian's usefulness by using it to specify security policies. We sampled 260 histories from the sequence of 5 new users and passed them to snapshot module. By doing this, we detected 27 security and safety violations, leading to 17 policies. Here's an example where gas stove was turned on when the user was away. And this safety violation is addressed with the policy gas stove should be turned off when the user is in home. The main thing to note here is that instead of manually imagining use and misuse cases for policy specification, Helian reduced the task to simply inspecting realistic scenarios. Hence, using scenarios allowed us to perform this task in a semi-automated and relatively grounded manner. Similarly, executing scenarios as test cases allowed us to detect subtle but dangerous platform and device flaws. For instance, we found cases where SmartThings dropped device actions and also instances where apps deleted by users persisted in the background, which can be bad for security. We also discovered that auto relock is implemented as inconsistent default by most door lock vendors. Although this was a preliminary investigation, this shows that Helian is useful for security testing. So now we know that scenarios are useful, but would these violations happen in end users' home? To evaluate whether scenarios generated by Helian are reasonably likely to occur, we performed 2 separate user studies with 16 additional evaluators. First, we wanted to test if evaluators would find the routines generated by Helian to be just as valid as routines generated by users. Our results showed that our routines were predicted to be almost as natural as routines predicted by real users, which means users actually found our routines to be reasonable to be configured in their homes. And more interestingly, the routines that we constructed using down flavor were seen as invalid by people. In fact, one of the evaluators even pointed out that the down routines seemed unsafe to them, which also encourages us to explore this down flavor more. Now we move on to the next question, that is, where we asked evaluators to rate how reasonable they found the scenarios generated by Helium are. So even without including the evaluators' data for training, Helium was successful in generating scenarios that were marked as being reasonable. Since most models are actually more accurate when you provide them with personalized data, we train the model with both the evaluator's routine as well as without them. As you can see, the accuracy improves after personalized data is included, which further speaks to the validity of scenarios generated by Helium. So in exploring how we could generate natural, useful, and valid scenarios of home automation, we learned several key lessons that we hope will inform future work as well. First, we learned that user-driven home automation can be treated as language, modeled as such, and leveraged to generate valid scenarios for security. Moreover, this naturalness is not only useful for security analysis and tasks such as policy specification, but could also be extended for modeling and predicting smart home behavior in general. Finally, our analysis of user-driven routines as well as IoT apps made one thing apparent. Unlike prior app-based systems such as Android, we can no longer study smart homes purely using apps published in marketplaces. People do not have to depend on developers anymore and can create their own routines directly using the UI. Therefore, we need to look beyond IoT apps and focus on the end-user programming paradigm that is being realized in home automation. With this, I conclude my talk, and I'll be happy to take questions.